Good morning, good afternoon, and welcome from wherever you're joining us. My name is Stephanie Vaughn. I'm the marketing director here at Vaughn Company. I'm pleased to welcome all of you to Vaughn Company's webinar, Thick as Sludge, Evaluating the Hidden Costs of Your Digester Mixing Process, presented by Steve Macumber, which unfortunately is why we are a bit late this morning. We do apologize. Steve's having some technical difficulties, but never fear, we had a backup plan in place. Mr. Eric Larson here, our senior process engineer, is going to be doing the presentation for you from here in Washington. The purpose of this webinar is to help you identify and capture the benefits of achieving a well-mixed, well-conditioned, and well-controlled digester. If you happen to experience any technical difficulties or a bad connection, please close out your browser and try logging back in. If you do miss any portion of this webinar, we will be placing it in an on-demand format on our website, on our Vaughn education page at chopperpumps.com/education. We will answer your questions and address any comments at the very end of today's webinar. If the answer to a particular question requires more detail or data, we will follow up with you after the presentation. If you do think of something after we close out the webinar, please email us at info@chopperpumps.com with your question or additional comments. There will be a few poll questions for you to answer today during the webinar, so please participate. We'd love to see your feedback. And I do know that each and every minute you give us today is valuable, so I would like to express my thanks to each and every one of you. Without further ado, I'm going to turn it over to Eric Larson here to begin. Thanks, everyone.
Hey, good morning, everybody. One sec. Did we manage to get Steve back? Am I seeing that, or am I? Okay. I'll just get going, and if Steve's able to join us with audio, get his audio working, we'll let him jump back in. But for now, I think we'll get started with the presentation. If we can cue the slide reel. Thank you. All right, Thick as Sludge, evaluating the hidden costs of your digester mixing process. Topics to be discussed: Vaughn Company overview of the Rotomix system, the value of digester mixing, standard success criteria for digester mixing, and what else could digester mixing systems do, followed by a quick summary and some Q&A. So a little bit of overview about the Vaughn Company. We're a fourth generation family-owned and operated company here in Montesano, Washington. We began as a tiny weld shop in Washington and helped dairy farmers with equipment. Started our business really in the ag industry. First patent issued was in the 1950s to Jim Vaughn, and the company was incorporated in 1960. We have over 30 domestic and international patents. And in 2021, we were really proud to be the award-winning manufacturer in the state of Washington from the Association of Washington Businesses. We have 35,000 units installed and supported globally with over 2,500 mixing systems. And we've completed about 1,000 CFD analysis on digesters and other mixing systems and hundreds of field verification tests. I'm giving you a little bit of overview of a full map range. We sell pumps all the way down from 50 gallons a minute up to in excess of 13,000 gallons a minute. And we're all operating out of what has become much expanded old Schaefer logging mill here in Montesano, Washington. We have just a massive holding of inventory, and in today's global economic situation, having inventory here domestically in the United States ready to ship to you when you need it is more important than ever. So Rotomix mixing systems, they're hydraulic mixing systems using fixed nozzles and external Vaughn chopper pumps. Rotomix design is a multi-zone mixing, which creates even mixing flow across the tank diameter. Its multiple discharge points creates even distributions of conditioned solids. No moving parts of digester, CFD experience in every system, and field verification experience to make sure that what you install is operating and commissions exactly as designed. Some of our previous Vaughn webinars, we covered various topics from wipes, designing for the new sewage reality, which was covering some of the more unique challenges facing our collection systems across the world and in the United States specifically. We have in the mix, dealing with indigestion. That's not a digester from the mouth, all talking about different steps in the digestion process and different influences that mixing and other operating conditions have on those processes. And then bypass the competition, avoiding cleanups with portable pumps, looking at our portable pump options and the importance of bypass for maintaining robust operations at facilities. Oh, and I will mention all of these are on demand at shopperhomes.com/education and also on our YouTube page. So the value of digester mixing. Why is digestion mixing important? And the answer is mixing is essential to the biological process. It's a large capital investment, and over and under mixing has consequences. It's estimated that the loss to the industry, to municipal and industrial digestion is more than $2 billion annually due to ineffective mixing. And this isn't just power costs. This is, decreased dewatterability, additional sludge disposal fees, additional polymer costs, all of these additive things that add to the cost of operating your solids handling process that add up over time during the multiple decades of operation of a facility during its design life. So what does poor mixing look like? Instability with temperature variance, inhibitory pH, anything below 7.0 is going to start to inhibit your methogen activity. And if you have poor mixing, you're going to see natural contaminants that are going to come through from your waste stream. You're not going to distribute those and dilute those. And there's a really old saying, the solution to pollution is dilution. And when we look at contaminants in our waste stream, to the extent that we can't remove them, we try to dilute them so they have less of an impact on our biomass and aren't as destructive to itself. And inconsistent gas production. When you have poor mixing, you're going to have kind of a boom bust gas production cycle where every time you feed, you're going to provide that contact, but you're not going to distribute that evenly. And so you're going to get an uneven biological activity rate and see uneven gas production rates that spike and lag as you feed and as your feed changes. And then operational challenges. We look at loss of volume from grit accumulation, scum surface accumulation, taking up headspace, foaming issues, and ultimately these can lead to digester upsets and unfortunately bypass.
Eric, this is Steve Mack. I don't know if you can hear me, but
hey,
you're doing great so far.
Thanks, Steve.
How's everyone doing? Don't you just love technology?
Absolutely.
So, hi, everyone. Yeah, for sure. So boy, do we look forward to getting back in front of everyone. We're so happy that you're here in this form, but I'll take over from here and continue on the way, as we've been doing. So just to back up a moment, just to stay where we are on this slide, but I just want to give you an overview. I want to go through, we went over a little bit of who Vaughn is and what's important about mixing. Why is it worth evaluating? How has it been done in the past? Sort of standard success criteria that has been used for years to compare any mixing system. Those criteria remain vital. Vaughn's very familiar with them and why they're important. We're going to go into some ways that the mixing system after that could help your overall biosolids program, sort of some value added things. And at the end, we're going to summarize. So I know we've already started here. Again, apologies for joining a little bit late. So we've looked at why mixing is important and sort of what poor mixing looks like. And we'll go on to the next slide if someone could go ahead and advance that for me. That'd be
sure
great.
thing. Steve, actually, to just give you a chance to get settled, we're actually going to just jump into our first poll question here. And I'll give us a second while you get settled back in now that you're able to get online. So the first question, what do you currently feed your digester? We've got a couple different options here: primary sludge, waste activated sludge, both primary and waste activated, and then some form of co-digestion, fog, high strength waste, food waste. We're kind of curious, those of you who do operate facilities that are joining us today, what are you working with in your facility?
Thanks for participating, guys.
Yeah, we're getting great participation here. Looks like a pretty good cross section.
Nice.
We've got about
I love answering these. I love asking these questions because it's always curious to me to get kind of that live information feed from people who are out there actually operating facilities. So what kind of variability is out there, especially from the side of the manufacturer or even, I'm sure there's a lot of consulting engineers around here that are interested in this breakdown. And it's kind of what I would expect. Got a mix of primary waste activated, but but definitely more combined, but the combined is not necessarily the majority. And I'm very happy to see that there's a lot of co-digestion going on. Very good stuff. I know that is a challenge for a lot of facilities, but the regulatory environment and changing dynamics are making that both a necessity and also more viable. And it's good to see that being represented in the numbers. All right. Well, thank you for that. Steve, back to you.
Absolutely, and yes, good stuff. Good poll information. I see that we have a majority primary waste activated blends, which isn't surprising, but certainly a process. So I'm going to move this poll out of my way here, and if we could, the next section of our presentation, we really want to go. We've talked a little bit about why is mixing important. I'd like to talk a little bit about next, how we design and verify mixing historically. So next slide. Historically, our industry has used different evaluation metrics that really focus on ways to design a completely mixed digester and then verify as best we can that it has been built. So starting out, historically, we start the design process with our spreadsheets, right? So we put information in, including influent, solid, mass, volume, what are the substrate characteristics, what are our target parameters for operations. Often we use some kind of biological process model, BioWin or Sumo are very common. And of course, on the design side, we can use computational fluid dynamics to really model velocities and shear stresses exactly as best we can, if it's done well, what's going to happen inside a digester, including any piping, interferences, et cetera, and actual geometry. On the verification side, once it's designed, of course, this is our biggest fear. The biggest fear is that we built it and now we designed for a certain volume and we're not going to meet our design requirements. So the design experience, including CFD and biological process modeling, is critical for partnering going forward. So in verification, we look at total solids. We can do a temperature profile. We can do tracer testing and different benchmark comparisons. So that just means looking at other installations that we've been successful with. Of course, that takes experience to do that. But next slide, all of that has to do really with understanding and achieving a completely mixed digester with a certain phrase that we use a lot, active volume. So something like 90% active volume is a phrase that we would typically see in a specification. So what does that really mean when we say that? So these techniques are really focused on achieving a minimum volume that's required to have success with the unit process. The volatile solids destruction that we're trying to achieve based on the specific rheology, the specific mix of blends that we're sending to the digester can only be achieved, let's say, with 1 million gallon digester. So we know from experience that we typically build in a roughly 10% margin of safety. So 1.1 million gallons, and a requirement of 90% active volume will give us what's needed in the biological model to achieve success and to meet regulations, to meet our permit. So although there's no clear industry definition of active volume, typical metrics that we look at are looking at a CFD and finding volumes, 90% at least, mixing velocities greater than 0.1 meters per second. We look at statistical analysis, solids, temperature profiles. That gives us an indication that yes, if we have those solids profiles that are consistent, we do have a homogeneous digester. So that's an indication. If we do tracer testing, lithium is an example. That's an expensive way to really verify that we have a thoroughly mixed, completely mixed digester. Although a good CFD design that's used is, in our opinion, in our experience, as good and worth pursuing. So again, active volume is just that portion of the total volume that's performing to the design criteria. Next slide. So next, let's talk about some traditional design criteria that's been used to verify that maximum active volume is achieved. Mixing energy is always been a big part of the story, but it is only part of the story. So we're trying to achieve a homogeneous mix for reasons that we've gone into in great detail in our other webinars. If anybody has any questions, again, please refer back to those or engage with us, and we'll talk about, you know, why homogeneous digester is important. But energy, there's different, you know, rules of thumb. WEF MOP 8, we've got Metcalfe and Eddy. These are basically horsepower per unit volume. They're similar. They're different units. One is gallons and one's in cubic feet. But we look at, you know, other processes may have different mixing energy requirements depending on rheology. And obviously many factors can influence, you know, how much energy you need, tank geometry, rheology, different obstructions. And again, that's where we have found in our experience that horsepower alone is not enough to just to build a digester, you know, considering CFD and all those other things. So next slide, please. These systems run 24/7, 365. So of course we understand that they're trying to have effective mixing with the least amount of power and the least operations and maintenance costs. And that has been a standard for many years. And we certainly, you know, we like to hit that one out of the park. There's other things that we're going to be talking about shortly, but once the digester is built, how do we verify? Typically, temperature profile, total solids testing is something that we do. Vaughn ourselves has performed over 250 of these on-site physical verifications. They can be done in a few hours. Typical acceptance criteria is looking for a vertical temperature gradient. At sample points does not vary by more than 1 degree Celsius. That's based on, you know, what's needed by the methanogens and, you know, the prima donnas that are doing their job in this digester as far, and again, total solid samples not varying more than about 10% of the arithmetic mean. So we look at those things. Again, that's all verification that our design is sound and we've achieved what we set out to achieve. Next slide. So what another tool, critical tool that aids in the design is a CFD model. So computational fluid dynamics, you know, we can easily look at different mixing system alternatives. We can vary the design, nozzle placement, where we're putting our energy. We can model unique geometry, sludge rheologies. We can look at, you know, with the non-Newtonian fluids, we can put in where the shear is occurring and how that translates into velocities. We can simulate tracer bursts, washout simulations. And the key there is doing this over time and having the field experience to verify that your CFD was correct and to sort of backfeed your future CFD analysis. So what we've seen at Vaughn is field testing has validated our analysis within 2%. And that just means that, for example, a washout simulation in CFD matches an actual, for example, tracer or temperature solids profile in the field. You know, if velocities are we're looking at 97% active volume in our CFD, we're seeing within 2% of that in the field. Next slide. Here's another example of, we got one more slide after this one. It's just, again, showing some of the velocities and sort of what we use to simulate and to verify that our design is going to achieve complete mix. We have a library of these available that we refer to. So chances are any project that's being worked on, we've seen a similar diameter or orientation or rheology, all of the above. If we have over 1,000 of these CFDs, you know, under our belt that we refer to, certainly some of them are available. We can perform a custom CFD as needed. If you have a large project and you really need that peace of mind, we can certainly do that. So really showing a couple of pictures here of sort of what these look like. There's certainly a lot more to it. There's an entire presentation we've done on CFD, so please engage with us if you have further questions.
All right. Hey, Steve, before we jump into the next slide, it's time for our second poll question. I just wanted to catch you here before we went into the next section. So this question, what issue do you most commonly experience? Scum blankets, foaming, poor VSR, and I kind of arbitrarily define that at less than 45%. Everybody's facility might define that differently. And then the I never have any issues, which hats off to you if you can honestly answer that. Looks like foaming is taking an early lead. I know in my experience that tends to be a pretty common issue that everybody struggles with and has really been a focus of a lot of research lately. I see somebody asking, can I put all? And I feel your pain. That's definitely, I've definitely, these all are issues that can happen and support each other in causing chaos for you and your operational plan for sure. Looks like the answers have stabilized and foaming is taking a very strong lead with scum blankets following directly behind and poor VSR. And it looks like we've got two people that have never had any issues. And good for you. All right. Thanks everybody for participating in that. Back to you, Steve.
Sounds great. I think, I'm one of those that put in never have any issues because I didn't see, microphone troubles for a webinar. So, but maybe you could add that in future polls. So let's talk a little bit about beyond. Now we've reviewed what typical metrics are. Let's talk a little bit about, hey, what else could your digester mixing system be doing for you, and how could you capture that in your future evaluations and sort of put a number on that value. So let's go to the next slide. So up to this point, again, we've reviewed why digesters are mixed, some of the traditional important ways mixing systems are designed and verified. It's all about achieving and maintaining active volume. And that is very important. So we're going to talk in the next few slides about a few things your mixing system could do to bring some real value back to your entire biosolids management project. So this includes dewatering downstream. So we know there's an impact on foam and scum management that has on operations and regulations and your impacts from gas collection, et cetera. We know that the understanding the behavior of how grit settles and how inerts settle in your digester is critical for any design, and we need to include that in our designs. And also the impacts downstream on dewaterability. So a digester, what happens in the digester also impacts downstream processes. So we want to talk a little bit about how we can capture that and discuss it. So next slide. So first slide here is a near and dear, and we saw in that poll that this is a common problem. We've done a specific webinar on the causes of foam and low density sort of scum accumulation at the top of the digester. There are many, many reasons for foaming events. Chances are more than 75% of anaerobic digesters nationwide or sort of globally will at some point experience a foaming event. There's so many reasons for that. Again, I'd like to point you to our previous webinars and how we can go into some details on the causes of that. But as far as mixing goes, there are some things that we can do. Obviously, keeping a completely mixed digester will minimize foaming events. That's what the system can do to help, outside of other forces. And with scum, we can do things to try to keep that layer incorporated with the entire volume. But those impacts are sort of qualitative, in terms of performance, gas production. There's operational costs, there's equipment, there could be potential structural damage that occurs from some foaming events. There's safety costs. There's real value there in keeping our personnel safe, not having slip and slide on surfaces that have been hit with foam. And regulatory standpoint, obviously, permit violations from an overflow, we want to avoid that. And worst case, insufficient volatile solids destruction. So these are the known sort of qualitative and quantitative impacts of foam and scum that we all sort of are aware of, but sort of how do we combat them with a tool in our toolbox with a mixing system. So next slide. So in our design at Vaughn, we have what's called a foam buster and a scum buster. So these are nozzles that are, in the case of a foam buster, it is located above the liquid surface. It has a splash plate. And what we're doing is showering a fan of sludge, high density, from the bottom of the digester through the pump. It's been conditioned with a chopping action, and we're putting that down on top of any foaming event. This can be valved and just be utilized as needed. But as we know, in many cases, we don't know when foaming events start. We don't always know. So typically this just runs. This is a nozzle that's just, it's not imparting any horsepower into the mixing energy. So again, we talk about previous evaluations where we look at horsepower. Vaughn has put this tool above, to combat foam, knowing that it requires some horsepower to move liquid through this nozzle, but its value is in physically combating foaming problems. Now we all know, looking throughout the wastewater treatment plant, where there's other areas in basins with foaming events, we typically find a way to spray a liquid, water, or what have you on top of that to physically knock down foam bubbles. So this is essentially what we're doing in the digester, and it adds value. We have some case studies that discuss that as well. We can share with you. Scum nozzles in a similar way. The picture on the right show the foam buster nozzle, and just below that, about a foot below the liquid surface, we would have a nozzle that would have be right in that low density scum layer that tends to accumulate to re-entrain and to bring all those floatables and that stratification, that low density layer, to bring it back into the total volume. So that is used with our Rotomix system, can also be supplement as far as other existing mixing systems to minimize foam and scum buildups. One other tool we have is to mitigate foam is a VFD, variable frequency drive. Offers some flexibility, allows you to fine tune mixing energy, current processes. A nice byproduct of that is it really can save up to 50% of energy costs, as we mentioned earlier. It's a critical part of any evaluation. We do recommend that for any digester application. There's studies that are going on right now, in some cases seasonally, with different types of microthrix or different types of foaming causes. Reducing mixing energy could be helpful. In some cases, there's current research going on looking at perhaps dramatically increasing mixing energy could help combat foaming that's caused by filament bacteria with some shearing action through our pump, et cetera. So we're looking at sort of cutting edge, what if this has been a problem for, I guess, forever with foaming. So this is just one more tool in the toolbox to help you combat that. Let's go on to grit. Now we've talked about this. It's obvious that grit management is critical for any digester, just due to a loss of volume, due to not meeting losing your volume, so you don't have active volume and not getting your volatile solids destruction. The energy requirements in most designs do not necessarily create the velocities to keep grit from settling. We've all seen these digester cleanout projects. They're often on a 10-year cycle or sooner. I know personally there are some large utilities that are more on a 5 to 7 year cycle of needing to really clean these digesters. If they don't do it, they lose their volume. Has some impacts on downstream processes, and there's a real cost involved. Obviously with that, it's more of a problem with sandy soils, but next slide. So what we've learned through experience, and my background in at Vaughn is even relatively large organically laden grit particles can have what's called a sand equivalent size that allows them to bypass modern grit removal systems. This means, think of a peanut M&M. That grit particle is the peanut, with the sort of the chocolate coating is the low density, low specific gravity organic material that's attached.
Ready for poll 3.
So, sorry, go ahead, Eric.
Oh, sorry. No, my bad. I didn't
No,
know.
no problem.
Yeah, bad timing. But I was having
Hot
them
mic,
queue up
hot
poll
mic.
3.
Oh, wow. No problem. So what we've seen is even with 100 micron, fairly modern grit collection system, when these organically laden grit particles, it could be a large particle over 100 micron, 120 micron, but it behaves as a much smaller particle. Now, once that grit particle is in the digester, it's going to start to digest that layer, and it's going to become more and more difficult to remove as it behaves like a larger particle. There's some studies going on right now that we would like to, we're participating in, but obviously mixing systems, including digester geometry, withdrawal points, must be designed with that sort of increasing effective grit size behavior in mind. And we like to consider that. Obviously, it's an important challenge to all digesters, but even over a 20-year evaluation period, just decreasing the number of digester cleanouts by 1 or 2 can have an enormous net present value. Easily, these cleanout projects can cost $250,000 plus, quite easily, and they can require the digester to be offline for more than a month. There really are costs beyond just paying a contractor to do this. There's operational challenge. You're not spending time on other possible improvements. There's procurement costs. Some of them may be insignificant for some utilities, and some of them may be quite significant, because this is time value of everyone's time within the utility, et cetera. So what we found, net result, if grit makes it to the digester, it really needs to have a pathway for removal, or it will accumulate. This CFD model on the right is showing velocities at the floor level. With our lower nozzles, all of our designs are typically mounted more nozzles on the floor, that we also, depending on the height of the digester, will have nozzles at a higher elevation. But we really focus energy at the lower level to get that velocity going down where grit could accumulate. So, and then with the rheology of sludge, that those velocities can translate upward. So just wanted to throw that out there, that we're quite experienced with grit, and wanted to bring it to your attention as well.
All right. Well,
so a mixing system, how can that, go ahead.
Hold on, Steve. We're going to jump into poll 3 here. So real quick, before we go to the next slide, we're going to jump in the last poll question. What do you wish to get out of your solids handling process? Do you want to see more stable operation? Are you hoping to get better cake solids out of your dewatering? More biogas production, or better grit or inorganics management? Grit and organics could be, ragging, passing through, you're screening into your digester. It could be issues with grit and deposition issues in your, not just your digester, but also your other various process vessels within that system and equipment. Kind of curious to see what we get here for answers. Looks like a pretty good spread. Something I was curious about when we were putting these questions together was the biogas production question, because I'm curious how many people are beneficially reusing their biogas, because obviously if you're just sending it to a flare, there's really no value in producing more of it necessarily, but other than the impact of it potentially reducing your volatile solids that you need to dispose of, and a better conditioned digestate. But looks like we've got quite a few beneficial biogas reusers, or at least I would assume to be, because that's the leading answer right now.
I'm certainly seeing that more and more.
Yeah, and that's a good thing. I think that is an untapped potential for municipal facilities, especially as we continue to expand natural gas use within the country, and see some opportunities for renewable resource generation. So
certainly, and obviously, yes, but the biogas is also a good point from Jim. Biogas is used for heating.
Yeah, cogeneration as well, and also coheating of the digester. Yeah. All right. Well, thank you for participating in the poll. Back to you, Steve.
Right on. So we're going to continue on with our third sort of value added area to consider when you're evaluating your mixer, to try to bring some of these costs back. in, with some real costs. We've talked about foaming and scum. We've talked about, how we can really have a focus on grit deposition. And now we're going to move into sort of downstream effects of how the digester mixing system operates that can affect and improve your downstream dewatering process. So cake solids are certainly influenced by digester health. Capture efficiency, solids recycling impacted by having a consistent digestate going to your dewatering process, whether it's a centrifuge, by a belt press, screw press, and those inconsistencies can directly and sort of from a human standpoint increase polymer demand. If we're going to have any kind of a test on polymer or belt pressures or any kind of dialing in of your system, you need to have a consistent product coming out of your digester, and obviously increase maintenance costs. If your systems are moving up and down and getting a lot dirtier and just under more stress, there's going to be more maintenance costs with them as well. So this is a common correlation that we've seen. This is from EPA process, manual for sludge treatment. It's a very general chart here, a graph of cake percent to volatile solid destruction. Or volatile solid percent. So got cake solids obviously increasing as volatile solids decrease. Now, regardless of whether this is a primary mix, blend, straight waste activated, these correlations are essentially similar, different angles, different slopes, but this is what we see. So maximizing volatile solid destruction is going to have a positive impact on your cake solids and how much polymer you have to use to achieve that. Similarly, the percent solids coming out of your digester thicker to a point is going to allow your dewatering process to achieve a higher cake solid. Now, having a higher cake solid or having a higher feed solids come out of your digester does make mixing with polymer a little more difficult, but the value is there if the digesters are operating well and we can get a high volatile solids destruction and get a relatively high feed solids. We see a benefit in terms of reduced polymer consumption and a higher cake solids. So as mentioned, having a consistent digestate to the dewatering equipment, percent solids, volatile solids is critical for optimizing any dewatering equipment. So if you're going to have a study on, optimizing your polymer or optimizing your belt pressures or back pressures on a screw press, or just trying to get the flows correct to whatever equipment you have, it's important to have a steady state, as much as possible flow coming in from the digester. And also, one of the things that a mixing system can do is sort of continually condition your sludge. So there is debris that builds up and re-rags inside a digester, and when that material, if it's large enough, can enter any kind of dewatering equipment, it can cause problems that require maintenance, shutting down, problems with polymer systems, mixing, etc. So keep that in mind. For example, one example of it with a 10 MGD wastewater treatment plant using recent bids on polymer, easily a 2 pound per dry ton polymer savings can represent approximately $30,000 per year. Your mileage will vary. Everyone sort of knows their own polymer consumption and how a pound or two or any change in usage could impact their bottom line. The point here being that, having a consistent, without the microenvironments of pH, not having a homogeneous flow coming out of the digester with total solids varying or pH, et cetera, can really impact how well that polymer, how effective it is. And then with your dewatering equipment, whether it's filtrate from a belt press, that can become dirtier and dirtier. One of the things we look for in dewatering performance is cake solids, obviously, but also centrate filtrate quality. So those solids that are in the centrate sent back to the head of the plant or into your solids processing are not removed. And typically the types of solids that are missed once, whether they're colloidal or for whatever reason they're missed by the dewatering process, can be missed 2, 3, 4 times. And they can really build up in your process and should be looked at and considered with your dewatering performance and how clean it's running and knowing that it can be impacted by or affected by your digester mixing equipment and your selection. So something we want to draw attention to, have you think about, and just consider when doing an evaluation. Let's summarize here. Next slide. So we've talked initially about, the importance of mixing. We've talked about the baseline sort of background for successful mixing. How important it is to create a homogeneous digester volume. All of this is very well known. We want the most homogeneous mixing with the low cost in terms of capital, operations and maintenance, power, well known. What we also did is added a few other features, some value added features. We know with a mixing system, we can think about, reduce the impact of scum and foam on your process. We can at least maximize the amount of grit that's kept in suspension and minimize that loss of volume by focusing energy and just being aware with CFD and our design with energy at the bottom, lifting energy that once grit has settled, the lifting energy velocities are much higher than the velocities required just to keep grit in suspension or entrained. You can think of a piece of grit lying on the bottom of a digester as sort of an airplane wing. As the velocity flows over the top of it, that's the lifting energy. But once it's in suspension, much easier, much lower velocities are required to keep it. So the goal there is let's try to keep this in suspension and remove it before it settles. And then, of course, stabilizing downstream dewatering processes. So brought up some points there. Again, there's much more to be explored on each of these. We want to bring them up here so we can ask more questions and really get to some specific costs for your application. So why use Rotomix? As you mentioned, this mixing system is one that can do more, and we think mixing systems can and should do more. Some of them are not obvious, in the past, but we hope we brought them up here as some things to think about. We have a flexible design for all different geometries and process applications, and a library of CFD models to sort of lean on to show that. No moving parts or maintenance inside the tank. No areas for rags to build up on different parts and pieces. So we minimize that, and it conditions the sludge best for downstream dewatering process by breaking down large particles, allowing that digestion process to go to completion for maximum volatiles destruction, and of course minimizing costs associated with scum, foam, and grit. With that, next slide. Love to open things up for questions. We got about 10 minutes to go here, so I think we're on track to take a few. Eric, do you want to jump in as well?
Yeah.
Yep. I'll jump in. This is Stephanie again. I am going to be reading the questions out loud to Eric and Steve, and they are going to go ahead and move forward with answering them. I'm going to start with the question at the top here that I'm seeing. Can you comment on energy calculations for blowers in comparison to active mixing systems like Rotomix?
Yeah, I can comment on that. So when you get into blower calculations, you get into two real aeration values that get defined. One is going to be whatever the oxygen requirement is. So what is that actual oxygen requirement, the AOR? And that's going to drive the minimum delivered oxygen that's required. But what often controls the amount of air required for a design is going to be based off of some mixing requirement. And generally that's going to be defined in some SCFM per 1,000 cubic feet or some of surface area or volume, some variation of that. And that's probably, a lot of that is defined by the various diffuser types and technologies regarding how they want to do that for different sludge densities, based on the bubble size, whether you're coarse bubble, fine bubble, all those things. What I've generally found looking at these systems is there's a pretty big disparity between the mixing aeration requirement and the actual organic aeration requirement for the solids destruction. And in reality, bubble mixing is very inefficient for the most part. So there is a lot of opportunity. It's something that we've really started exploring and are working on. We've developed a couple different projects working on this concept, but having that diffused aeration or some other type of aeration, and then using Rotomix to actually drive the mixing requirement. And we've seen opportunities to provide 25, 30, 35% energy savings over a traditional aeration mixed system. But there are also situations where the mixing and the biological oxygen demand are pretty similar. And so it's kind of a case by case basis, but that's a very great question. It's an interesting topic.
Okay, next question. Somebody wants a reminder of what VSR means.
Volatile solids reduction. And we're usually pretty good about not getting too jargon specific in these presentations. Apologize for that.
Next question. What process cases are not recommended variable speed?
So processes that wouldn't be recommended variable speed are going to be, so the first one's going to be blend tanks. Anytime you're blending, especially if you have a continuous feed operation from that blend tank, which I would recommend if at all possible, you want to have a consistent best mix that you can have in that tank. There's no value in reducing below that optimal mixing energy for blending. Where in a digester and other process tanks, you might have a difference between a suspension or settling management mixing energy and a biological contact energy, where you might have some value in a VFD varying that energy level, or variable level tanks where you're varying that level based on the level coming up and down, where you're it's not as important that you get that blending perfect all times of every day. And then long-term sludge storage. So anywhere where you've got restrictions on land application and you're storing sludge for long periods, rather than a VFD, we would much rather you do an on-off staged operation if you're going to try to not mix fully. If you are doing a sludge storage that's just an EQ, an equalization tank for your dewatering process, that's also something where you'd want to treat that almost like a blend tank because of the impact it's going to have on your dewatering equipment to have a more stable feed that isn't stagnated. Yeah, go ahead, Steve.
All right, I'll just jump in. I would also add that even with a digester on VFD, we would recommend for grit management maximum power at least 2 hours a day, roughly.
Yep.
Eric, you may correct that to be more specific, but we even with a VFD, we like to maximize the power to the mixing system a few hours a day, regardless.
Absolutely, and generally we'll recommend starting out for new systems, starting out 24-hour 60 hertz full speed operation, and then as the system starts to stabilize, you can start lowering that mixing energy for portions of the day, and see what that does to your lab results on your digesters. So if you're doing your volatile acids, alkalinity tends to be the best for looking at that, but you can also look at your pH probes, your temperature probes. Are you seeing drops in your temperature variance? Are you seeing issues with pH mediation? Are you seeing your volatile acids start to increase, your alkalinity to start to drop? Those are signs that you're maybe losing stability, and then you can start say, okay, we've gone as far as we can go here. But there are a lot of systems that can go to say 22 hours a day at 45 hertz, which from a power standpoint represents about a 55% reduction in power, for a majority of the day, and then ramping that back up to 60 hertz. I'll make a comment for anybody who may have our systems or use them. Getting an entire digester volume takes up to mixing speed when you turn the mixing system on takes quite a bit of time. It's a lot of volume and mass to try to move, and a lot of inertia. And so if you're going to stage on and off or make any start and stop changes, understand that there's a lag time between making that change to the mixing operation and the actual mixing flows in the digester. So if you're trying to overly fine tune that to say 10 or 15 minute windows, you're really not getting up to, you're not really moving too far. You're kind of baselining an average. And that's probably not what you're trying to achieve when you're doing fine adjustments like that. So if you're ever in doubt, especially if you have one of our systems, feel free to contact me or contact Vaughn, and we can help coordinate, and because we want you to be as successful as you can be in your process.
What dewatering technologies do you have in mind here?
Steve, that's for you.
Have in mind which dewatering technology do we have?
I think they're asking what dewatering technologies are we referencing here? I think the answer is just talking about it in general.
Yeah, in general, all of them are influenced by consistencies in digestion. So filtrate, centrate, polymer, although they vary for different technologies, they're all impacted by how uniform and consistent that sludge is. So the intention there was to sort of talk in general. I mean, we can talk specifically on a phone call about how each technology sort of responds to different consistencies, but the intent was to be general.
Okay, I'm going to kind of combine the next two questions here. How is preventative maintenance performed on the mixers and motors once installed inside the digester? And the next question is, how do you unplug these internal mixers?
Yeah, so that's kind of a two-parter, but so the systems are designed to be no moving parts in the tank. And so all of the wear and maintenance items that are going to have service lives that are less than the service life of the tank between cleanouts are going to be outside of the tank. So all of your wear items on the pump, the motors, all of that pumping equipment and mechanical equipment that's rotating and is driven is all external to the tank. The pumps are back pull out. Everything is easily worked on and managed. And that's by design, because the last thing you really want to do is have to enter a digester or do anything in a digester, because those costs can get very high very quickly. We do a lot of groundwork in each of our systems to understand what's going into that system. And because we're using a chopper pump that is as reliable as the Vaughn chopper pump, we're actually able to dictate a solid size and adjust the nozzle selection to make sure that we're providing a nozzle that is going to be able to pass the maximum solid that will pass through the pump. And so our systems are designed to not have any plugging issues. And the nozzles themselves are warranted for 10 years. That isn't to say that there haven't been situations where that's happened. Generally, when it does happen, though, it's due to outside influence, either construction debris at startup that creates an untenable condition that's outside of the operational parameters, major changes in process, like a long-term screen bypassing of a facility, or other issues that take us outside of the design parameters for the system. And in those cases, generally the systems are able to operate with one or two nozzles out of operation, either due to plugging or other issue, without too much problem. But ultimately, the tank will need to be taken down and those nozzles cleared. But that's a fairly rare situation that happens, and generally it's due to something that's outside of operational parameters happening external to the digester.
Thanks. What is the max DS content that Rotomix can handle with municipal sludge and with biological waste?
Ooh, that's a great question. And that gets into, I saw another question about how do we deal with rheology and how do we adjust for that? The answer is it depends. Different sludges have different rheologies at different solids content. So dairy manure and that type of waste, because of its consistency, you can actually go 10, 11, 12% solids and still have a very pumpable fluid, where if you were looking at some sort of Frankenstein polymerized thickened sludge that's at 9, 10, 11% solids, you're going to be dealing with something that is like cement. So there's a lot of variability at different solids kinds. I would say generally 6 to 7% thickened polymerized sludge is as good as we can go, and that's really pushing it. With THP sludges, thermally hydrolyzed sludges, such as Canby, Pondus, those types of technologies. You're looking at the sky's kind of the limit on those 12, 13, 14%. Whatever you're going to see out of those processes, we're generally going to be able to mix. But you're also going to see a very high volatile solids reduction rate, and that average solids in the digester drop pretty significantly. And then, outside of polymerized or like special thickening technologies, you're really going to be hard pressed to feed anything higher than 6% into a digester without polymer or some other additional pretreatment step. And we can mix those no issue. And we have a library over 100 sludges that we've had analyzed for viscosity plots. And we actually feed those into our analysis and provide those viscosity curves with our reports so that they can be benchmarked.
What is the maximum height of the digester for proper sludge mixing?
There's no real limit. I mean, there's a practical limit of materials of construction for the tank. And you do run into some issues related to gas solution and other issues when you get really, really tall, 70, 80, 90 feet tall. But there's really no restriction necessarily for these systems in that regard. You can go as tall as your site and tank construction and engineer will allow you to.
How much does digester geometry, diameter to depth ratio impact mixing system design?
Oh, a ton. It has a huge part to play. It's one of the reasons why regulatory bodies always fail to specify a tight range of what mixing energy should be. You can have a really wide pancake, 100 feet in diameter and 12 feet deep. And you think about all that surface area that's robbing mixing energy from the volume. You're going to need to have a higher input energy to mix that. Generally, what I recommend is your radius to height be 1. So that ratio of radius to height. So if you're 60 feet in diameter, be 30 feet tall. If you're 80 feet in diameter, be 40 feet tall. Sometimes you may not be able to go that tall. You might, but that tends to be the sweet spot. And that really gets back to, kind of hydraulic radius. I don't know how many of you have a background in that, because that's more of an open flow channel design concept. But when you look at how do I have the most volume with the least amount of surface area? Like, how do I get as much volume in my digester with the least amount of tank surface area to rob energy from a mixing system? That's where you're going to get your highest efficiency. And that's my recommendation.
And I kind of think you might have hit this, Eric, but it says you mentioned sludge rheology impacts on CFD modeling. How much variance do you see due to sludge blend and or solids concentration on rheology? Mm-hmm. And how do you account for that in design of your mixing system?
Yeah, I think the best way to describe it is it is a log relationship or an exponential relationship, in the sense of, as you increase your digested solids, the viscosity and the mixing energy required to mix goes up exponentially. So as you go from a 4 to a 6% solid in a digested sludge, the rheology goes, like, let's say the viscosity doubles. If you go from 6 to 8, another 2% increase, it might quadruple. It is a very steep curve there. And so, you can see how you could get into trouble if you're not carefully analyzing that when you're going into the design and specification of the mixing system, where you're not providing, like, let's say, the difference between a 6% polymerized thickened sludge and a 6% conventional sludge is a lot. And I've done some presentations, and there's some information on some of the other webinars. There's a nice chart. I'm trying to think of which specific webinar it's on. but that shows the actual viscosity plots, and it's an exponential increase as you go up in solids concentration. And polymer has the same effect as that. And actually, interestingly, THP, there's a good rule of thumb we've developed that seems to bear itself in the data, is that if you have thermally hydrolyzed sludge, whatever that solids percentage is, you can treat that as a sludge, as a conventional sludge with half that concentration, and you'll be about on the mark. So a lot of facilities, we say, yeah, you can double your total solids input if you're going to add a THP process, and your mixing system will still be more than capable.
Very important.
Pressure gas mixing versus submersible mixer versus sludge mixing. Which is best for biogas generation?
I mean, you really get into, so I'm not a big fan of gas mixing, just because in a world where rapid rise and foaming are issues, the idea of introducing gas back into the sludge just doesn't seem like a great idea to me. Not to mention the maintenance headache that can exist with the hydrogen sulfide issues in those systems. I just am not a fan. I know there's people that have those that like them, but I'm just not. It's not something I would want to have to operate if I was managing a facility. The outside of that, it's not necessarily that that other technologies don't work, but you just have to look at kind of the pros and cons. I think there's absolutely a place for submersible mixers. And we actually manufacture submersible mixers and both vertically mounted mixers as well for different applications. But I think digesters, because of the nature of it, submerging something in the sludge is just not a fun experience. The maintenance becomes really challenging, especially getting access to that equipment if you have any motor failures or issues, the potential for contamination into the digester of various components and things like that, and have to fish those out during a clean out. It's just what happens if you have something get dislodged and it gets sucked into your heat exchange loop? What happens to that? There's just a lot of things that I'm not a fan of. Now, that being said, there's a lot of people who swear by them. So, your mileage may vary, but I think what we really want to see is digesters be properly designed. I truly believe that in a world where digester mixing is being properly specified for the design criteria and for good operation, that we will be a compelling alternative. What I don't want to see is a race to the bottom in trying to provide false efficiency by making these processes less manageable and less operationally viable. And that's what I feel like I see in a lot of projects now, is kind of basically a bidding war of who can say they'll do more with less. And I don't think anybody wins in that.
Okay, I think we have one last question here. Do you have other performance criteria like velocity magnitude shall be greater than 0.1 ms at 90% of digester volume for a successful mixing?
That's where we're at right now. I think we found that for the flow field that our mixing system provides, if we can see 90% above 0.1 meters per second, that's going to translate to a successful tracer washout. That's going to be a successful total solids test. And we're going to be able to show both in CFD and in physical testing that our system is meeting spec for a 90% active volume. And that's something we're comfortable with, but that's very empirically defined. There's nothing theoretical that says that that's the gold standard. That's actually a research area that I'm very interested in pursuing, of how can we better dial that in to provide something that becomes a universally accepted benchmark so that we can get a better apples to apples comparison of what we're doing in the digestion space. It's something that I'm very passionate about. But I do think that as of right now, that's the best we have as far as specification.
Thank you,
All right.
Eric. Thank you, Steve. So before I do my closing message, I'd like to turn it over to Steve if you've got anything you'd like to close out with for the group.
No, I just really appreciate everyone's time and look forward to supporting your needs in the future. Looks like I'm getting a notice here that I'm not in the audio, but I'm not sure if I am or not. But really appreciate everyone's time, and please reach out if we can help you further.
No, thanks, Steve. And thank you again to everyone for joining us. Please don't forget, if you have more questions or have any comments you'd like to share after we close out the webinar, please email those to info@chopperpumps.com. And then in about a week's time, this video will be up on our education page at chopperpumps.com/education. One last note I'd like to share with you guys. Please visit us at these upcoming conferences. We'll have a booth on the exhibitor floor. We'll be at the Design Build for Water Wastewater in Orlando, April 4th through 6th. We'll be at the Waste Expo in Las Vegas, May 9th through 12th. We'll be at WEF Residuals and Biosolids, May 23rd through the 26th. We will be at many more after that, including WEF Tech. So please come see us. We, again, really appreciate your time that you shared with us today. Thank you and take care, everyone.
Take care.